about statistics, and we're going to look into this idea of how useful, how powerful, how reliable is the information that we're actually gathering from the statistics. Another video talked about being able to identify the value of n, or the sample size that is needed in order to be able to trust the results. What I really did there in that other video was I just kind of derived where that formula came from and alluded a little bit to why we would use it or how we would use it. I wanted to go through that a little bit more and talk some stuff about those different pieces and how n, or the sample size, fits in with all this stuff. So to start with power. Power is the probability of rejecting H naught when H naught is not true. Another way of saying that is the probability of rejecting H naught when HA is true. Right? It's how often are we going to actually make the correct decision. Right? That's what we're referring to in that particular instance. And so this is how powerful is the test we're actually running based upon sample sizes. A lot of times what we're going to do with that. So we're saying n equals, say 10. And if we use n equal to 10, how reliable is the result when the sample size is 10? And a lot of times we think, well, 10 is just way too small for a particular result. But depending on what we're doing, maybe it's okay. Maybe it's not, though. Significance is your alpha level, meaning what is the value that we're going to choose in order to be able to say, yes, this is acceptable. Most of the time, that is defaulting to 0.05. If you want a higher significance level or lower significance level, depending on how you're processing this, the idea is maybe you want to make it 0.01, which means you're dealing with a 99% confidence interval, or maybe depending on how you set that up. But anyway, this is in this case it'd be a 95% confidence interval, or 90% confidence interval. You're talking about just not being equal, right? So there's two-sided and there's one-sided. And if you're talking about a two-sided test with a significance of 0.05, then you're talking about a 90% confidence interval. Anyway, the idea, though, is that this is the level that we're going to predetermine of what we want to occur, meaning we want a significance level of 0.05, and if we get a value out that is less than 0.05, we reject H naught in favor of HA. That's the significance. That is also connected to a probability as well. And there's going to be a whole other video that goes along with this, talk a little bit more about why and how we use some of this information. And then we have the effect size, which is essentially the difference between the wanted and expected, or the ideal and the actual. It's this idea of the difference between X naught and our X bar and mu, right? So what's the space that we're actually looking at? How much difference is there between those two places? So let's just kind of talk about an example for a second. So let's just say we have our hypothesis is that mu is equal to 0. And our alternative is that mu is equal to 0.8. Now, a lot of times we just set this up and we'd say that mu is not 0, which is a two-sided test. So here, if we're saying the significance level is 0.05, that's alpha. In this case, since it says not equals, you're looking at this and you're saying mu is equal to 0.8. But you got to remember that the original statement here was mu equal to 0. So what we're actually looking at here is that mu doesn't equal 0. So this is a two-tailed test, which means that our confidence interval here is, we want to put that in there, our confidence interval is 0.9 or 90%, right? That's what we're dealing with in this instance. So we're looking at a confidence interval of 90% because it's a two-tailed test, because we're saying mu is not 0, because we're actually picking that mu is 0.8. So in this particular instance, our effect size is 0.8. So let's say we have a scenario here where we're talking about maybe a sweetness scale of some sort. And 0 is the taste testers are looking through and they're saying, okay, this tastes exactly as sweet as it should be. 0.8 is how far away the testers are saying the sweetness is. And there's either positive or negative. It's in both directions. It's either too sweet or it's not sweet enough in terms of what they were expecting. I don't know how all that works out. I'm not a foodie in that perspective. But the idea is that we can measure this somehow. We're trying to quantify that. And we say, based upon this, a difference of 0.8 in the expected, this is the point at which people are going to start to notice that it's not as sweet or it's too sweet from what they were wanting, right? So one of the things we might do is we say, well, if we have n equal to 10 and segment e equal to 1, Since sigma equals 1, we're assuming standard normal, right? That's going to make the process a little bit easier. And we're saying n equals 10. Okay? So if n equals 10, sigma equals 1. And then we say, well, what does that tell us? Well, we go back to that formula we had a second ago that we were talking about, is n is equal to something squared, right? So that was some value for z times 1. In this instance, we're going to divide by 0.8 and we're going to square it. All right? Now, with the thing we have going on with this one, this is going to work out in this particular instance, the way this is set up with the value of z and all this other stuff. And I'll leave you to kind of process and build up some of these other pieces. You're going to end up with this being equal to, in this instance, you're going to end up with it being greater than 10, right? So what does that mean, that it's greater than 10 when you run the numbers here, okay? Well, it means that 10's not big enough. Okay, so the way this actually works out is that we end up, when n equals 10, we end up with our power here being equal to 0.81. Right? Now, why is that significant? Because we're looking for 0.9. We got 0.81, which means that when we do this stuff right here, we don't have a large enough population or a large enough sample size in order to get the confidence interval that we're looking for, right? So we don't have, this test with 10 in it doesn't have enough power for us to trust the results. That's what that comes down to and means. Now, there are softwares out there. You can use R, you can use Python, Minitab, all sorts of different things out there. There are even ways you can force Excel to do this as well, to run these numbers and say, well, when does it actually become viable? When does the test? How many values of n? And actually, the place that this works in this particular setup, the way this is set up right now with mu or our alternative being 0.8, n has to be at least 14 to have a confidence interval of 0.9, right? So in order for us to reach our significance level of 0.05, the power has to match 0.9 in this instance. In order for the power to match, we have to have a sample size of at least 14. There's a bunch of math that runs through this as you do this, and I'm not really necessarily as concerned with that as much as the overarching idea here of what's going on. And the way we do this by hand is we just start plugging values in until we get this to work. Now, I have this set up, right? So all you got to do at this point is actually plug in the value for z here, right? So we go back and we find the value for z. You can look at your z table and grab that out and find out where two-sided 0.9 is, right? And you plug in that value for z right here, and you'd be able to figure out what the corresponding value. It should be 14-ish when you come back with that value. And like I said, there are programs out there that'll actually run a whole bunch of values for you and do this process for you. And as we start to, and this is another big piece here, if we start to change this, right, if we say that our significance level is 0.01, well, guess what that does to n? N has to be much larger than 14, right? Has to be much larger. So the lower the significance level is, the higher the confidence interval is, right? Or the bigger the confidence interval is, which means the bigger the confidence interval is, the larger the sample size needs to be. Okay? If we reduce, like in this instance, this came out to be 0.81, if I remember correctly when we ran the numbers. With 10, yeah, it's 0.81, right? If we had lowered this down to 0.1 as our significance level, this would actually work. We could accept this if we're saying we have a significance level of 0.1, which corresponds to a confidence interval of 0.8 or 80%, which is pretty low. So we normally wouldn't do that. But that's the meaning behind what we're working on, what we're doing here. Okay? I hope this was useful. Please reach out with questions, comments, and let me know if these are working for you. Okay? Take care.